presentation comes from John Biddescombe from CSCS.
Okay. Morning, everyone. I'm John Biddescombe from CSCS. I'm presenting work from what we call ourselves the DLAF group, a bunch of us working on solvers and task programming. How do I advance slide? Okay. The motivation background behind this work today is, I should introduce the title. What we're looking at is how we've integrated MPI into our tasking system, and to make things interesting and potentially quite dull for you, we've used the latest C++ standard to make it future-proof is the idea here. We've been doing task-based programming for quite a few years at CSCS. Previously, we used HPX, which I guess many of you have heard of. HPX is actually a pretty big library, and it includes a whole bunch of stuff for doing distributed task graphs across multiple nodes. And it was based on futures. And futures are lovely, we like them, they're very good. But the C++ committee eventually decided to drop futures from the future plans and instead use something which is called the standard execution or senders framework. And it basically does the same as what futures used to do, but it has a slightly different API and a slightly different way of handling things. And so we forked HPX and created a library called pika, which targets standard execution, and basically we just stripped out all of the threading runtime from HPX, kept all the bits which are, the efficient scheduling of tasks, the execution, threw away all the distributed stuff, threw away all the futures, and then put back distributed by just wrapping the MPI stuff that we used to have in HPX, but this time wrapping it in a senders framework, and that's what I'm going to talk about today, and some of the things that don't work the way you think they would, and things that do. And the driving application behind this is a library called DLA Future, which is a distributed linear algebra library. And it uses the pika tasks. It does computation on the CPU. It has GPU support. And I don't mention it on these slides, but in fact, most of the abstractions we're using for the C++ standard, the senders type of thing, we're actually doing the same with CUDA as well, but I'm not going to go into that on this because it's just, this is too much to say. And so all the MPI communication is wrapped in C++ senders now, and so the API that the user sees is a little different from the conventional one, but you'll see in a moment. And the real question we wanted to answer is this: is there a best way to handle the scheduling of the MPI in our task graphs? And is the new senders API, is it any good? I mean, does it do, does it do what it says on the tin? And the spoiler alert is, yeah, basically it's fine. And of course, the question of why are we choosing the C++ standard, it's really just back to this old question of how do you future-proof your applications if you want them to run everywhere and work with decent performance. And of course, everybody uses CUDA, HIP, that kind of stuff. Those are great, we still use them. OpenAC and OpenMP I'm not so keen on because they're based on pragmas, that kind of thing, directive-based programming. SYCL, it's kind of vendor-based. Cocos is nice, obviously we like that too, but again, Cocos and the standard have slightly diverged, and Cocos is trying to move back towards the standard, and if we just use the standard itself, and one day Cocos will adhere to the standard, we hope, then everything becomes, what's the word I'm looking for, easily integrated. And the standard is actually, the senders API is written in such a way that it's decoupled from the implementation. It's an API. And as long as everybody uses that API, because of the way it's implemented, it uses templates for this, templates for that. If somebody in Cocos came out with a complete implementation of the standard with Cocos backends, then ours would just plug into it and it would work out of the box. And as a demonstration, for example, I have Qt-based applications where I have a scheduler which transfers tasks onto Qt threads for doing GUI updates, things like that, and it just integrates completely smoothly with no changes to your code. The standard API that you use for doing our task-based programs runs there, and the GUIs updates, and it all integrates very smoothly. It's very nice. You all know about task graphs, and we like them because they encourage you to write your code functionally so that you do a piece of work, you pass the results to the next, and you build your DAG up that way, and you avoid races and locks, and you hopefully improve scalability with the aim The aim in mind being that I'll skip a slide. The aim in mind that you can keep your queues full of work and execute things as efficiently as possible. And it's interesting that the CUDA graphs, the guys who came up with CUDA graphs, well, NVIDIA were the first people to push the Senders API for C++26, and it fits very nicely with their CUDA graphs. In a way, it replaces the CUDA graphs. And actually, we're not using... Most of the time, and for reasons I'll explain to do with the dependency chains of how our data is passed around, we're not actually doing things with graphs directly on the GPU. Most of our stuff goes onto the GPU and then back to the CPU for coordination, and then back to the GPU, and there's quite a lot of going on in between because of the way the dependencies work. But in principle, the graphs will run just on the GPUs if you chain things, and maybe I'll mention that again, but if you specifically say this work runs on the GPU and then that work runs on the GPU, those will both run on the GPU without coming back. And so inside Pika, for managing the tasks, like all the other runtimes, and I'm assuming you're familiar with this kind of thing, is we have cores in NUMA domains, and there may be many of them. And each core has got a little scheduler running on it, and it's running on a bare kernel thread, an OS thread. And of course, what you do is you have work which is sitting in a queue, and you have a context switch when you take a task off the queue, but it's not an operating system level kernel context switch. It's a lightweight task, meaning we just effectively switch the stack frame, switch a few registers, execute the function that represents the work in that task, and then when the next one comes, we do that and on going, which means it's a more efficient way, and you don't have to have quite so much overheads on the operating system. So that's a kind of conceptual overview. And Pika, HPX before it, supported multiple different thread pools. You can have, what I'll discuss in a moment is a pool dedicated just for doing MPI work. And does that make things better than doing things on the rest of the cores, or does it actually, I mean, if you split work off into an MPI pool, your cores are left free, but now everything's funneled through one thread, that kind of thing. And in the senders world, there's some difficulty explaining the word scheduler here because we have schedulers running on our, managing the work in our task queues. But the senders API actually calls the thing which creates an execution context a scheduler as well, but it's a different scheduler. We used to call them executors, and you can have a C++ scheduler which targets a core or a NUMA domain or a socket or a thread pool or anything you like. It's up to you. The API doesn't specify. It's up to you to implement these things. So that kind of gives you the overview of how things fit together. And I'll try and explain how we've got it running. This is an example of work going on in the Cholesky, and here you can see we're keeping the queues pretty full. We're doing the work. There are tiny gaps in between these tasks where things are being switched in and out, and as the DAG starts to thin out at the end, we've got gaps happening here. I'll mention that again in a minute. But basically, it's quite efficient. It does the work it's supposed to do, and it works very nicely. And of course, this is the CPU, but the same thing's happening on the GPU, and we're coordinating tasks just to keep the queues in the GPU as full as we can as well, but I don't have any pictures specifically of that. The Senders API, just to summarize, what makes it interesting is that it differs a bit from the old futures in the way you actually coordinate work, how you create tasks and then how you launch them. There was the futures worked fine. Senders are slightly more explicit in the way that you have specific commands to create a sender chain, specific commands to say, I want to transfer that work from this thread pool to that thread pool, or from this execution context to that one, depending on what your execution represents, this socket, this NUMA domain, that core, that core. And then to build the DAG up, you can say, when this finishes, then do that, or when all of these finish, then do that, or execute a bulk launch of a whole bunch of tasks. And when they all finish, then do this. And so the syntax is basically the same as the old futures, but the way you implement it is slightly different. And you have an explicit method for launching, which you didn't have with futures. Futures, in a sense, there was always an unnecessary synchronization because you didn't know whether this future had started or whether it was still waiting to start. And if it was still waiting to start, you don't need to synchronize. You can attach continuations to it. Whereas with senders, you have a sender, you attach everything you want to it, and then you launch it. So there's no need for synchronization before the launch point, which makes things a bit cleaner and nicer. And, you know, those extra microseconds that you save, they all add up. How do we actually wrap our MPI stuff in senders? Well, don't feel like you have to follow these lines of code that thoroughly on, especially the stuff at the top, but anything which is a function, and the final parameter in that function is an MPI request, which basically fits all of the MPI I send, I receive, I barrier, I this, all of the non-blocking MPI calls follow a convention, which is quite useful. They always have the MPI request at the end. And so any function which is invocable, if you attach a request to the end of it, we can effectively wrap in our little API, which is just very, very simple. It's basically 5 lines of code kind of thing. And so what the user sees here is, I want to do an I send. And so they say, give me what we call a transform MPI, and I'm passing these parameters into it. And so you say, I've got a buffer, a size, a type, a destination, the usual tags, and a communicator handle, and I want to do an MPI send with those. So just give me a starting sender. The just is a special C++ keyword now, or a library word, I should say, rather than a keyword. So you say, just give me this bunch of parameters, pass them, and just returns you a sender. And now pass that sender into the transform, which is our one that we've implemented in our library, and that sender will then operate on the MPI I send, and will effectively attach those parameters to it. But the extra thing it'll do is it'll stick an MPI request on the end. And when that has done whatever it's supposed to do, then execute, and you can put whatever you like in there. Now, in this particular example, I've said release the message buffer, just to show you that you can effectively pass in something, do the transform, the MPI transform, and then when it finishes, you can then say clean up after you. In fact, most of our buffers and things are reference counted, so we don't need to bother it. What happens is MPI transform will take a reference count if necessary, keep that thing alive, and then when effectively you're guaranteed the lifetime of your buffers until the task has completed and returned back to you. And start detached is a sender-specific way of saying, start this task running, and I don't actually care what the return value is, just detach from the return. And that will then go off into the thread queues, do its stuff, and Pika will handle that. Now, a rather curious thing that we've done in DLA is that because it's a linear algebra library, and the matrices are split into tiles, each tile is actually wrapped in a sender as well. So you can say, iterate over the tiles of a matrix and do some operation on them. But when you say, give me that tile, you're not actually getting the tile itself, you're getting a sender to that tile, which means if somebody else is using that tile and they've got exclusive access to it, your code will effectively block at that point. And blocking in Pika doesn't mean blocking, it means suspending, going back into the task queue, doing some other work. When whatever you were waiting for becomes available, it gets woken up, it comes back, then you continue. So what that means is that whereas if you had algorithms running effectively in parallel but sequentially, as you would see in this plot, I've lost the mouse, there he is. If you imagine 1, 2, 3, 4 algorithms running here, in DLA, if the first tile triggers tasks on 2 other tiles, and it triggers tasks on these other tiles. These tiles are now available for more work. And so when a tile at the start of some algorithm becomes available, but then there's a second algorithm which is supposed to operate on the result of the first algorithm, it can actually begin before the rest of the algorithm has completed. So what you see here is 4 Choleskis happening one after the other. And this is a contrived example just for the purposes of demonstration. But what you can see is that instead of each algorithm starting when the full everything else is finished, they're able to kick in as soon as the blocks they need are available. They can say, oh, block 3 is ready, I can just start going because I needed block 3. Because effectively your DAG actually has the accesses to all the tiles that you want. And you can see here, we've got one dedicated thread, which is just doing all the MPI communication in this particular case. And that just sits there doing that. And what we do is we keep all the work off that thread. So just to see what can go wrong, I'm just going to check the clock so I don't go too long. Just to see what can go wrong is, inside each of our cores is running a little scheduler with an execution thing happening. There's a little loop which is basically saying, give me a task, execute that task. Oops, I beg your pardon. Give me a task, execute that task. When it's finished, go back, take the next task, execute it, and just keep doing that over and over again. But we'd quite like to poll for MPI as well. So we can throw in a little polling section in here. So then the question is it better to have, let's suppose we've got 64 threads on some of our nodes, 64 cores, I should say. Is it better to have 64 cores all polling, or is it better to just have a separate pool where we just put one dedicated thread with MPI and we just do the polling on that one and we keep all the work off it? And the thing to watch out for is that anything that happens in this execution here, if, for example, you block something, you go into a suspension point here, or you actually call an MPI function and you take an OS lock, you don't just block this task, you block the whole OS thread here. So you've got to be a little bit careful about what you allow and what you don't. As a case in point being that if you have a loop and you say, send this, send this, send this, send this, send this, and the first send blocks for some reason, those other threads, those other sends, they don't happen. So you might, for example, say, well, instead of just doing a send, what I want to do is transfer that send onto the MPI pool and send it from there, and then you can then continue with the other sends on this thread that you're doing. And you have to be a little bit careful with how you manage blocking the other tasks, and that's kind of what we're looking at here. Is there's lots of different ways we can do this. We can either do everything on one thread, do things on multiple threads. We can transfer this issuing of our MPI calls to one thread. We can transfer the execution of the completions. The problem here is the sender API. If I am an asynchronous piece of work and I finish, when I finish, I call set value on whatever my, if you say when that finishes, then do this, I have to call the function which executes the then. And somebody has to do that. Is it me who does it, or is it some other thread that does it? Who decides? And it's we have to decide which thread is going to do that. And that's why we like the sender API, because you can be very explicit about when that finishes, then execute this piece of work on that thread, or do it on the same thread you're already on, and you can put this in. So when a poll for an MPI feature says, yes, that request is ready, we have to call the callback, which represents the then or the when or the whatever it is we're doing. And so you call set value, and now we can explicitly say transfer this somewhere else, or we can execute it directly. And I'll come back to that in a moment. And of course, we have to be careful what we put in this main task here to guarantee forward progress, because we don't want to stop this loop happening. And it turns out there are some times inside MPI where we accidentally, we basically do have blocking, deadlocking problems that we didn't expect, which I'll come to in a moment. So the first implementation that we put in, there's a function in pika, which is just called yield while, which you say, I want something, but it's not ready yet. So what I'll do is I'll test to see, is it ready? No, it's not. I'll just put myself to sleep. And then the task, something else will be pulled off the queue and executed, and I'll go basically back on the queue. And when I've bubbled through the queue and I come back into execution, I'll then check, is that thing I wanted still ready, or is it ready yet? And if it's not, I'll go back on the queue, and I'll just keep doing that until the thing's ready. So if I'm doing a polling for an MPI request, I basically say, is that request ready? No, okay, go to sleep, do some other work, and you just keep bouncing around. And that actually works very well, because as soon as that task is ready, as soon as that request comes back as saying, yes, done, the task that wants that is me. And so I'm ready, I can just run. There's no latency, I just execute immediately and I carry on. So basically there's no new tasks created. I basically say, go to sleep, no, not ready. And you keep going to sleep, waking up, and as soon as you wake up and the thing that you wanted is ready, you just carry on, and off you go. So the latency is very low on that, effectively, notwithstanding the fact that you've put yourself to sleep. And something, I put myself to sleep, that task might not actually be ready right now, but I can't do anything because I'm asleep, and it's only when I next get woken up that I can take action. The downside of this is that there's quite a lot of, if you put yourself to sleep and then wake up and put yourself to sleep, and that happens many times, and you've got 64 threads doing that, you've actually got quite a lot of pressure on the queues. There's lots of queues, managing all this stuff. And you don't want to accidentally, you don't want to just waste time on all those overheads, and you have to be very careful about forward progress, because if I'm a task and I'm constantly putting myself to sleep and I never wake up for some reason or other, I can cause blocks that were unexpected. A slightly improved version of that might be a suspend resume. It's exactly the same, except instead of putting myself to sleep, waking up, testing, putting myself to sleep, waking up, testing, and just repeating that, put myself to sleep once, wait till somebody else says, that thing you wanted is ready, and then wake me up. That works very well as well, except that when I get woken up, I have to go back on the queue, effectively, because I'm a task, I'm asleep, I'm in a queue somewhere. Somebody says, you're ready, and it wakes me up, and now I'm back on the queue, and I have to work my way back to the front of the queue. And variations on that. Less pressure on the queues, but a slightly longer latency before I actually get executed. This is a kind of obsolete implementation that we tried, where we said, instead of having the thread itself put itself to sleep or suspend itself, or rather, this is what happens on the execution of I've missed an explanation, but really it's this part here. When you call set value and you execute what's happening here, there's a crucial step, which is that here I'm inside a task, and tasks have they have a wrap around them. They have their own stack frame. You could have task local storage, like thread local storage, but bound to a task. There are certain things which exist inside a task. The polling loop here, in most of our operation, is outside of a task. And if I now trigger set value on a task that's in the queue here directly, I haven't done a context switch, and I haven't put myself into the correct task frame. So we have a mode of triggering continuations, which we call new task, which no matter who triggers the execution of this continuation when an MPI request becomes ready, we always create a new task and we put it on the queue and off it goes. And what this means is that you never get any problems with blocking, and we always allow ourselves, for example, if you issue an MPI request and you say, I only want you to do work on the MPI pool, and so I issue my MPI send and I say, on the MPI pool, do an MPI send. MPI pool does things and it tests and it says, oh, the request is ready. When it gets the continuation, it explicitly transfers back to the main work pool and it doesn't execute on the MPI pool because I've put in a new task. I've said a new task, and I've specifically said here, schedule that new task on the default pool, not on the MPI pool. And the reason why this is slightly obsolete is because the next one I'll show you in a moment. If I explicitly say, put this work on the MPI pool, and when it completes, transfer back to the default pool, but in the default pool, I've actually used this, I can actually end up creating two tasks, one which transfers back to the pool and one which then transfers back to the pool again, and I can wrap tasks in tasks in tasks, which are so obsolete, but I leave it in because it's a useful abstraction. Continuation basically means when you have a function, you say, when this task is ready, then execute that. Back to our picture from before, when you execute the continuation, if you don't transfer back from the MPI pool to the default pool, you might actually end up in a situation whereby this line here, which shows the MPI pool here is basically empty. But if you had a continuation on this little red block which says, when this triangular decomposition finishes, then do this reduction to band or something, then that would happen on the MPI pool, unless you specifically say, go back to the main pool. So we have to be careful about transferring threads from one place to another, and I'm going to have to talk fast now. Some guys in America added an extension to OpenMPI to say, instead of testing for requests, you can actually hand a callback to MPI, and it will execute the callback for you. Same problem. On which thread is it going to execute that? We can handle that by essentially saying, when that callback comes in, we can add a transfer. And we have four possibilities. I want to make an MPI send. Do I do it myself, or do I give it to the MPI pool? I can either transfer, or I can not. If I do it inline, it means I do it myself. When the completion comes, I can do it inline, like execute it immediately, which means it might be happening on the wrong thread, the MPI thread, or I can say transfer it back to the main pool. So you've got four combinations there. On top of that, I can try and reduce the latencies by saying when the completion comes in, transfer it back to the M pool, but do it as a high priority task, so it goes to the front of the queue, not to the back of the queue. So I've got three options there, which give me 8 possibilities. And then I've got I can use yield, I can use suspend, I can use new tasks, I can use continuations. And you can actually put all of those into just, this is why we like the sender API, because I can effectively put, I've actually got 64 different ways of handling tasks being dispatched and triggered. And they effectively are wrapped inside. If the requests are in, oh, I beg your pardon, that wasn't supposed to happen. Effectively, I've got 2 combinations here, 4 combinations, 8 combinations, and then there's a whole bunch of different ways of dispatching which are specified somewhere else. A benchmark, which just spawns tasks, saying send something to the next rank, send something to the next rank, round in a loop. And then, so this one sends to that one, sends to that one, it goes round the loop, and it does that n times, but every node starts one, and it goes round and round and round. Downside of senders is you can get a huge explosion in the number of templated, because each sender, when you say do this and then do this and then do this and then do this, they're effectively chained function calls, and you get types which they completely destroy the debugger. I'll skip through that. If we do the ring test and we just run it on a single rank, you can see that now I have to explain here. You can see up here I've got request, transfer, continuation. I don't know how to stop that. Request, transfer, continuation inline, request inline, continuation inline. So down here, we've got continuations inline. Across here, we've got requests, we've got transfers on the request. So every time I do a send or a receive, I'm giving it to the MPI pool and saying, you issue the request. And so you've got 4 combinations here, multiplied by, there's effectively another 16 or whatever it is, combinations of different ways of doing things. Doing things in line, requests in line and continuations in line here, you can see these are basically no ops because we're just sending to ourselves, so MPI is exiting very quickly. Over here, you can see effectively the difference between these bars is the cost of spawning tasks. And when we start adding more ranks, you can see that we actually see the effects coming in, and everything's about the same. Small messages, nothing's really happening. If we go to big messages, the gap again is bigger, but something weird happens here, which is that turns out MPI isn't as non-blocking as you think it is. The suspend resume and the yield while, because they don't create any new tests, when you switch to a large messages, it switches from doing an eager protocol to a rendezvous protocol. It's internally taking some locks, and these things start blocking. And so we can't use these modes in the general case because they just don't work. Turns out in our loop of continuations and graph has got cycles in it which at some point or other are causing this to block. I'll talk fast and skip over that. If we go to the daint and we do the same on there with much more, here we go to, in this case we're doing a whole bunch of 4x4, 16 ranks on 4 nodes with 4 nicks on each node. Same problem comes out. We have messages here, messages here. I ran a check to see if OpenMPI behaves the same. It also does. So something we learn from this is that doing continuations in line is dangerous because we can potentially escape from our loop in the polling thing. So the right-hand side of the graph we should avoid. And it turns out we should avoid this quadrant here and this quadrant here where we're doing requests transferred and continuations transferred is wasteful in terms of overheads of sending tasks from one queue to the other. And this quadrant down here is our sort of sweet spot. In fact, we're actually using these modes over here as our defaults at the moment, but I'm going to encourage us to switch to using these modes over here as our default. And OpenMPI. This is the test where we use the OpenMPI continuations, where we actually attach them. And what we're really trading for is we're trading how efficient is the MPI polling compared to how efficient is our polling. And it turns out that our polling is about as good as the MPI polling, but I have to say when we use this, our polling loop is just so much simpler because with MPI doing all the polling, we don't have to maintain queues with all our requests in. We don't have to maintain locks for different threads doing stuff because we just give it all to MPI and it handles it. So the fact that the OpenMPI extension performs about as well as ours is like, okay, that's great because that's less work for us. So when that becomes part of the standard, we'll use it. I'll skim through some quick benchmarks. This graph is missing because the rest of the jobs, they're still in the queue because I didn't realize we wouldn't have access to the machine for, I ran a bunch. This is a kind of, this just shows you the difference between, for example, a good mode that we use and a bad mode that we use. You can see the difference is actually quite noticeable. It gets less as the overheads start to dominate. But this is, for example, just one graph of a Cholesky. And this code over here is whether we're doing things inline, transferring, inline transfer, blah, 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 high priority, low priority, those kind of things. And also, we have a lot of situations where tasks don't complete. Because it turns out our task graphs have got more cycles and deadlock opportunities in than we thought. And so basically, these modes here are the ones we're going to have to stick with. And I'll cut short the explanation of stuff that's missing over there. But the bars represent whether we're using a custom pool or no pool, whether we're using a high priority or not a high priority, different colors there. Overall, the main thing that we've noticed when we've switched to doing the polling in a dedicated loop, instead of using the previous yield while approach where we suspended and resumed, is the jitter has just gone a lot down. Things are much more predictable in the sense that this isn't a particularly illustrative example. This is the generalized eigenvalue solver, and this is a breakdown of the different sections within it, how much time they take. The blue one here is interesting because we still have one blocking call in our reduction to band, which we try to get rid of, but so far we have, I can't see them out there. This line here is when we use our yield while effectively, this is where we use a blocking call, and this is where we put things on the asynchronous stuff. Now, on that one particular algorithm, it makes a big difference. Overall, it doesn't make much difference, but all the same, it still hurts. This is a comparison with other solvers. You can see the blue line is our DLA. It's beating Slate and it's beating ELPA up to about, what was this, 2 to the, I can't see, that's 2 to the 2, which is 4 times by 4, 16 ranks, I guess, on 4 nodes of Daint. I should be honest and say that if we extend that graph out for some of the test cases, we actually start to do a little bit worse, but that's things we'll improve on. CP2K, which uses a slightly different API, we have a C API wrapping it. We're currently doing better than the opposition, but again, if we extend things out, it might not be the case. I don't have all the results here. Conclusion is that there doesn't seem to be a one-size-fits-all in terms of whether it's best to use a single thread or multiple threads or do things inline or do things with continuation. It kind of varies around a bit, but for most of the stuff, just doing things using, I would say, doing things using, essentially, you want to do requests in line and transfer everything back off the MPI pool and do continuations back on your work pool. And wherever possible, use high priority threads for things that are, working. To be fair, what we should do is allow every single MPI request to be treated differently. But I haven't gone to the trouble of putting that into the code because it's horrific, really. But the real conclusion is that we actually like the C++ API, the Senders API, and we really would like MPI to actually stop using 1980s style kind of, when you use the OpenAI MPI extensions, it's like time traveling to 1980 because you have to pass these sort of C-style function pointers and that kind of stuff. Just give us a C++ API. With that, I'll stop and you can all have lunch.
Thank you, John.